Hey, what's up everyone? Welcome to the start of our third unit, which is states of matter. Today we're going to go over intermolecular forces, which is one of the most important topics in all of chemistry. So I hope you can get a lot from this video. Let's start by defining intermolecular forces. So these are going to be forces that occur between molecules and keep them together. So while you might have things like ionic and covalent bonding, within the atoms that are keeping them together, within the molecules themselves, you're going to have intermolecular forces that keep them together. And so these intermolecular forces tend to be weaker than ionic or covalent bonding, but again, they are everywhere and they're constant. So that constant weak force is what's keeping everything together. The existence of intermolecular forces can be seen if you look at like this heating chart right here. This is the heating chart of water, and you can see it starts off as ice. And as you increase temperature over time, the temperature increases. So remember, temperature is just like a function of how fast the molecules are moving. So as time goes on, as you increase the temperature, the molecules start moving faster and faster until they get to a point where they can't move any faster unless you start breaking the intermolecular forces. So at this point, although you are increasing heat, temperature doesn't increase because the molecules are currently working on breaking intermolecular forces before they can move faster and faster. And so after they break a certain amount of intermolecular forces, they can now move faster, faster again. And that's where you see, the heating of liquid water. And then after that, you get to that point again where you can't go any faster unless you start breaking those intermolecular forces. You should note, though, that during these times, you are still adding heat. It's just that heat is, being used to break those intermolecular forces. And then eventually you get to a point where you have broken enough intermolecular forces that you can now create steam. And so in this heating chart, you can see those plateaus are what represent the breaking of intermolecular forces. So intermolecular forces generally tend to be Coulombic interactions. And so Coulombic interactions are interactions between two charged particles. I think everyone knows these kind of intuitively. You know how if you have two positive particles, they're going to repel each other. Same thing with two negative particles. But if you have a positive and a negative particle, they're going to attract each other. And that force of attraction can be mapped using this equation right here, where force equals K, which is some constant, times Q1 times Q2. Q1 is the charge of the first particle, Q2 is the charge of the second particle, over radius squared, or the distance between them squared. And so, like if we say there's a +1 charge here and a -1 charge here, Q1 times Q2 of this little interaction right here would be -1. And generally, you can compare the Coulombic interactions between two charged particles. So I can say two particles, like if we had a particle that was +2 being attracted to a particle that was -2, these guys would have a stronger attraction than this. Even though we don't know the K value or the R value of either of them, we know that the Q1, Q2 value of this one is going to be -4, as opposed to the -1 value of these circles right here. And so that means the attraction that these face are going to be stronger than the attraction that these face. So again, we're going to see why these are important a bit later on. Don't worry if you don't understand this right away. But let's take a look at the specific intermolecular forces that I want to go over. And so there are going to be 6 of them, and they're listed from strongest to weakest. We're going to do ion-ion, and then ion-dipole, dipole-dipole, which is going to include hydrogen bonding, and then ion-induced dipole, and then dipole-induced dipole, and then London dispersion forces. So let's get started with ion-ion. Ion-ion is one of the most simple ones. It's purely Coulombic, in that a negative particle is going to be attracted to a positive particle. And these are going to be like your ionic solids, like such as NaCl. And so basically you have these negative charges being attracted to these positive charges. And since it's purely Coulombic, that's why ion-ion attractions are going to be your strongest intermolecular forces. So pretty simple. Let's move on to the next one, which is ion-dipole. So what is a dipole? A dipole is a molecule with an unsymmetric distribution of positive and negative charges. So let's take a look at both these diagrams. In this diagram, you see that the oxygen is going to pull on electrons from the carbon. But the thing is, there's a oxygen on both sides, meaning the pull is the same. It's kind of like a tug of war. If both sides are pulling with the same force, then that means you don't have a dipole, because that means all the positive and negative charges are split evenly. But if you look at this over here, you can see that, you know, the people on the top are pushing greater than the people at the bottom. And so you have a negative charge here and a positive, slightly positive charge here. And these are what these symbols mean, by the way. So this means a electronegative, kind of like an electronegative pole over here. And then this means an electropositive pole. So there's another diagram here, and where you can see that those charges. And so basically what's happening is that you create, if I were to make like a really crude drawing, it's basically like if you have a negative charge here and a positive charge here, almost like you know, like a magnet. And so if you introduce some negative particles or some positive particles here, they are going to face attraction. So these are going to be attracted to each other, and that's going to be attracted to each other. So that's why we call it a ion-dipole force, because if you take a dipole and you take ions, they're going to attract each other, and they create this whole network of attractions. You can see like a really cool diagram there that shows how these are constantly forming. They are weaker than ion forces, but they are pretty strong when it comes to, you know, general intermolecular forces. So our next one is going to be a dipole-dipole force. And so imagine that dipole that we just took, and we introduced another dipole. And you can see how they are going to attract each other. And so basically what happens is that you create this massive network of these dipoles that are working to maximize attraction while minimizing repulsion. And so these are the third strongest intermolecular force, but they are only about 1% as strong as covalent and ionic bonds. So it goes to show how much harder it is to break apart ionic bonds or covalent bonds rather than, you know, intermolecular forces. A specific type of dipole-dipole force that is pretty important is a hydrogen bonding. And so a hydrogen bonding is a dipole-dipole attraction where a hydrogen is electrostatically attracted to a highly electronegative atom. And there are three highly electronegative atoms where hydrogen bonding can occur: fluorine, oxygen, and nitrogen. And I don't have an acronym for this, surprisingly. I just remember FON, like as if it's like a name, and that just works for me. I don't know why. But you have to take a look at why this happens. Why hydrogen and these three in particular, why do they create stronger dipole-dipole attractions than usual? Well, first of all, it's the electronegativity. When you have a dipole of this super electronegative atom with hydrogen, you create a really strong dipole. And so when you have stronger dipoles, you can have stronger attractions between other dipoles. If it helps you think about it in a certain way, think about like a weak magnet and a strong magnet. So in hydrogen bonding, you have like a really strong magnet, as in comparison to other dipole-dipole attractions, which may be, you know, some weaker magnets. The second reason is the fact that hydrogen atoms are extremely small. And so what does that mean for the molecule? Well, that means when you create these forces, you can get really close because the hydrogen atom is really small. So these molecules are like tightly packed and they're right next to each other, and that minimizes that R value. Remember our force equation here. When the hydrogen atom is extremely small, this R squared value is exponentially less. And so that's why hydrogen bonding in particular is such a strong dipole-dipole attraction. A lot of the times people say hydrogen bonding is going to be like your strongest intermolecular force. Well, I mean, it's not true, but generally this is the most common one that you see happen a lot. And so just remember, hydrogen attracts to fluorine, oxygen, nitrogen, and if you have those, you're going to have a hydrogen bond. So our next one is going to be an ion-induced dipole. So when an ion induces a nonpolar compound to turn into a dipole for a small moment of time, we call that an ion-induced dipole. Think about a nonpolar compound. So an even distribution of charge. So let's say, you know, the electrons are dispersed pretty evenly. Pretend that's even, because I don't think that is, but whatever. And imagine you introduce a positive ion into the mix. And what happens is that this positive ion starts pulling at those electrons. So what you see happen is that this nonpolar compound kind of turns polar for a bit. And basically you have something like this, and that ion has caused this nonpolar compound to turn into a dipole for a small moment of time. And that is basically what an ion-induced dipole is, because now we have a force between these two. This has become like a dipole, and then it's attracted to this positive atom right here, a positive ion right here, and that is a dipole. Sometimes these induced dipoles can occur on their own. So we're going to look at dipole-induced dipoles. And so by random chance, a nonpolar molecule can have a temporary dipole moment. So imagine you have a molecule here, and it has an even distribution of charge. But you have to remember that these electrons are not, in one place. They are constantly moving. So let's say by random chance, this nonpolar molecule gets more electrons on this side than it does on the other side. And so what does this mean? Well, you have to remember that this molecule is surrounded by many other nonpolar molecules. And so let's say we have this, right? And it's another nonpolar molecule with an even distribution of charge. Now, this molecule right here has created a dipole. And the dipole from this molecule is going to induce a dipole in this molecule. So this is going to turn into 1, 2, 3, 4. The electrons are going to move away from this side onto this side in order to maximize charge and minimize repulsion. And so you see how a random event caused a temporary dipole moment, and that dipole caused another dipole. And this dipole will cause another dipole, and so on and so forth. And this constant dipole, forming is what you call a dipole-induced dipole. This brings us to the last intermolecular force that I want to go over, which is a London dispersion force. So these are constant formation of dipoles to create a weak intermolecular force that holds together all compounds. And so London dispersion forces are interesting because all compounds are going to have London dispersion forces, but some molecules are going to have more London dispersion forces than others. And so how can we predict the amount of London dispersion forces a molecule can have? Well, in general, as atomic number goes up, so does London dispersion forces. So remember, London dispersion forces relies on the electrons, in a nonpolar molecule to polarize. So that means, be on one side as opposed to another. And as it turns out, the more electrons you have, the more likely it is that by random chance, more electrons are going to be on one side as opposed to another. So we say as atomic number goes up, that's what the Z means, polarizability goes up. Meaning how likely is it for by random chance for there to be more electrons on one side than another? How likely is it to be a temporary dipole moment? And so as that polarizability goes up, so do London dispersion forces. And remember, as a general trend, as all intermolecular forces rise, including London dispersion forces, you're also going to have an increase in boiling point. Remember, boiling point is just like a function of how much intermolecular forces you have. So let's try to do a bit of practice concerning all of this. First of all, what is the principal intermolecular force that must be overcome when N-hexane C6H14 is vaporized? So C6H14 is a nonpolar molecule. And so it's not going to be, first of all, it's not going to be hydrogen bonding because you need one of those fluorine, oxygen, or nitrogen, and you don't have any of these here. So it, by default, cannot be hydrogen bonding. B, covalent bonding between the carbon atoms. That is not an intermolecular force. That's what we call an intramolecular force. M-O-L-E-C-U-L-A-R. And so the difference between intra and inter is that intra is between, and then inter is between like the molecules themselves. So it can't be B. C, dipole-dipole forces. That cannot be true because in order to have a dipole-dipole force, you need them to be polar. And as we know, C6H14 is a non-polar compound. And so by default, it has to be D. But a general trend about London dispersion forces is that it's going to be most dominant in non-polar large molecules. And C6H14 checks those boxes very well. And so the principal intermolecular force is going to be London dispersion forces, and we are correct. Let's move on to problem 14 of 2017. the normal boiling points of molecular fluorine, chlorine, bromine, and iodine increase in that order. Which of the following statements accounts for this increase? Actually, if you look at fluorine, chlorine, bromine, and iodine in the periodic table, you're going to see that they're going to be right on top of each other. So fluorine, chlorine, bromine, and iodine. And what does this tell us? Well, as we know, as you go down a periodic table, the atomic number increases. And as we know, as you increase the atomic number, you're going to have more and more London dispersion forces, which is going to cause an increase in boiling point. So let's see which answer choice best portrays that. First of all, the chemical reactivity decreases in that order. That's not true. They're in the same row. I think it's not a row, it's a column. Group, it's called a group, right? And so elements in the same group are going to have similar chemical reactivities. So it's not like their reactivity decreases in that order. London dispersion forces increase in that order. That is true. That is a possible answer. Let's look at the next one. The dipole-dipole forces increase in that order. That's not true. These are just, molecules on their own. They're not going to do dipole-dipole forces. And then D, hydrogen bonding. You don't have hydrogen. You can't have hydrogen bonding in these. And so the only answer that makes sense and the most logical answer is B. And that is the answer. Let's go on to the next one. In which are the ionic solids ranked in order of increasing melting points? So remember, ionic solids are going to follow this equation very heavily. So Q1, Q2 over R squared. So basically, we're trying to compare which ionic solids are going to have greater forces. And so remember, we don't know, we can't figure out the K or the R squared of any of these compounds as is. But what we can do is we can compare the Q1, Q2 values. Molecules with a larger magnitude of Q1, Q2 value are going to have more intermolecular forces or stronger intermolecular forces than molecules with lower magnitudes of Q1, Q2 values. So we have 4 compounds, KBr, NaCl, NaF, and MgO. So let's calculate the Q1, Q2 values of all of these. K is going to have a +1 charge, bromine has a -1 charge, so Q1, Q2 is going to equal -1. NaCl, Na sodium has a +1, chlorine has a -1, so again Q1, Q2 is going to be -1, NaF +1 and then -1, and so Q1, Q2 is going to be -1, but then Mg has a +2 and oxygen has a -2. And so that means our Q1, Q2 value is going to be -4. And -4 is the greatest magnitude of all of these, meaning MgO is going to have the most intermolecular forces. And as we know, as you increase intermolecular force, you also increase the melting point. So that means of all of these answer choices, the one that shows that MgO is going to have the greatest melting point, that's going to be the answer. And thankfully, there's only one, and it's going to be A. Because MgO is the greatest out of all 4. And we're going to go with A, and that is the right answer. Let's go on to the last one. The lattice energy required to separate the ions in an ionic solid of magnesium oxide is much larger than that of LiF. What contributes the most to this difference? So remember, lattice energy is going to be about intermolecular forces of an ionic solid. So chances are you're going to have to look at this equation again. Q1, Q2 over R squared. So let's compare those Q1, Q2 values again. In LiF, you have a +1 and a -1. So Q1, Q2 is going to be -1. But in MgO, as we just calculated, you're going to have a +2 charge and a -2 charge. And so that's going to be -4. And so the principal reason why the lattice energy is going to be greater is because in MgO, these are going to have charges of 2. But in lithium fluoride, you're going to have charges of 1. So let's see which answer choice best represents that. Mg is a smaller ion than lithium, and oxygen is a smaller ion than fluorine. That just does not, it's not very relevant. Let's look at B. Fluorine is more electronegative than oxygen, and lithium is more electropositive than magnesium. I mean, this would make a difference if we were, looking at like dipole energies or dipole forces. But again, we're looking at ion-ion forces, so this doesn't really make sense. C, MgO contains doubly charged ions, while lithium fluoride contains singly charged ions. This totally makes sense. This is basically what we saw here. These are doubly charged ions, and then these are singly charged ions. And so C does make sense, so I'm going to keep C. And then MgO contains more electrons than lithium fluoride. That doesn't really mean anything. The only thing that would, I guess, contribute to is probably London dispersion forces. But again, in an ionic solid, London dispersion forces are going to be, pretty insignificant as compared to, their ion-ion interactions. So D does not make sense, and it's going to be C. MgO contains doubly charged ions, while lithium fluoride contains singly charged ions. And we are correct. Alright, that's all I have for this video. I hope you learned something, and I hope to see you in part 2 of States of Matter.